Hello everybody, it's me, Alan. I hope everyone is doing well and staying safe through the outbreak of COVID here in Westmoreland. I just want to talk a little bit about my paper on Schrodinger's equation, partial derivatives. I basically wanted to write it in a way that anybody could read it, but that a more studious or interested person would be able to also gain a lot of knowledge from it. The several books I read either started doing like examples and explaining the energy parts of it first, or they started from the whole opposite end and went into the theory first. So I'm like, you know what? I read all this stuff and it's like I don't even know what you're talking about. And then they're like, oh well, in 4 chapters we'll get back to that. I'm like, no. So what I do first here is I define everything that I feel you need to know just going into the paper, or you're going to get confused and not know what the hell you're reading. So I have 15 definitions and functions at the start, and I will add to them if I'm typing something up, I'm like, okay, I wouldn't know what that is. So moving on, the second part is the theory, proofs, and showing its relations to older physical models in relation to classical mechanics, which variational. Well, you wouldn't know. So, well, I'll get more into that later. So, and then of course towards the end we have worked out solutions, example problems, graphs, and models, which I actually have one here. Well, no, I don't have it here. Don't worry about it. I'll show it to you in the class if you want it. Alright, so as far as what my paper wants to do, 3 things. First, to break down the equation piece by piece. Like I said, define everything. The second part, like I said, it's showing the proofs, going through the origins of the history, all the relations. And the third part, just to show the applied examples of the equation, explore current research, new discoveries, and future possibilities. So, if you didn't really know a lot of the advanced mathematics, you should just really have a proper understanding of basic calculus, maybe some experience with linear algebra, differential and partial equations, probability and statistics. Should know what complex variables are and what vectors are, which, reading that now, it's like, okay, maybe you do need know a little bit of advanced mathematics, but that's just really to understand more of the theory part. I think you could read the non-math parts and still understand most of it. At least that's my goal. So, very first thing, we define the Schrodinger's equation, which is I, the imaginary unit, times h bar, which is the reduced Planck constant, and multiplied by the partial derivative of the wave function with respect to time, and you set that equal to the Hamiltonian operator times the wave function. So, what's the reduced Planck constant? That's h bar is equal to h over 2 pi. H is approximately 6.62 times 10 to the negative 32nd joule seconds, and that's the quantum of electromagnetic action. And this is equal to a photon's energy divided by its frequency. So, what's a wave function? So here, and we start with the general wave function in multiple dimensions, where we define the wave function to be big psi of r and t, and that's equal to little psi of r times the time operator big T of little t. And the little psi is also a wave function, but just with respect to position and with no spin in 3 dimensions. So big psi is also in 3 dimensions. If you want to just focus on 1 dimension, just replace r with x to represent position. And of course we can do this, well, I guess not of course to you guys, but of course we can do this for measuring for momentum with P. So what does a wave function require? It has the 4 following properties. The probability density is the square of the function. It must be defined and continuous at all points. It must be differentiable, and it must be square integrable. Integrable. So in regards to the left-hand side of the Schrodinger's equation, we will take the partial derivative with respect to time of the wave function. And what is a Hamiltonian? Well, the Hamiltonian, represented by h hat, is equal to h bar squared divided by 2 times its mass times the Laplacian square plus v of x, which is the potential energy. Of course, h bar is the reduced Planck constant, and the Laplacian square, Laplacian, I can't, however you told me to pronounce it today, Laplacian is, well, we can define the Laplacian operator as a second order derivative, so that's the square, it's not squaring it, it's the second order derivative, and you typically define it in 3 dimensions, but it can be used for any n amount of dimensions. Yeah. So for in 3-dimensional space, the Laplace square is equal to the second partial derivative of x plus the second partial derivative of y plus the second derivative of z, which are the x, y, and z coordinates for the 3-dimensional plane. You can modify that as needed for higher and lower dimensions, like I said. Just bumping it up, say, or would that be bumping it down to 1 dimension? Would be h hat is equal to, I'm sorry, it's negative, I missed that in the first one, these screens are hard to read, but negative h hat square, or h bar squared, divided by 2m times the second differential of x plus the potential. So I think I have taken enough of everybody's time. I hope you've learned something, and if you have any questions, of course, ask. There's a lot more, and it would take me a long time to read it all, so see ya.